Welcome to the last lecture in AP Biology for this year. Last video lecture ever? This is the end of chapter 50. Tell me, which one? 3. Very good. Makes me happy to know you know what chapter we're on. The end of chapter 53. It's 4 sections, and we got 14 slides plus a little extra slide for a reminder or suggestion. The last time we talked, I introduced the idea of exponential growth and a formula, and we talked about some of the details of that formula. Today, I'm going to show you kind of the more useful formula and the one that would more likely show up on a AP exam question. And we're going to talk about what's called logistic growth. And this is much more of a mathematical model that represents how populations really deal with their environment, because it includes a variable we haven't talked about yet, which is which variable? K, capital K. So this component of the equation is different from the just straight exponential growth equation. And the variable K is the new variable, and it stands for carrying capacity. All right? And there it is right there, carrying capacity. K, and this is something you probably want to note because this variable actually comes up later kind of on its own. K, or carrying capacity, represents a maximum population number. Let me rephrase that. A maximum sustainable population number. Okay? So it represents the highest number, ideally it represents that, the highest number of individuals you could have in a population and keep that level of population for a sustainable long period of time. You could probably have 5 trillion people standing on planet Earth, but I don't think there's any way for us to feed and provide water for all those people.
So 5 trillion isn't the sustainable?
Now, that's a great question. What is K for the global human population? What is the human carrying capacity for Earth?
1 trillion.
1 trillion? 7 people? 7 billion? 8 billion?
Right now we're at 7.3 billion.
We're almost at 8 billion right now, and we have no idea what K is for the global human population. Scary bit of trivia? We could be over it.
Oh no, we're gonna die. We're all gonna die.
It could be a disaster. We could still be under it, which would mean we could continue to grow. We actually have no idea. And for humans, it's a little bit weird because I don't think any other animal or plant or living thing deals with this. What is a factor that affects how many people can live on Earth? How many humans can live on Earth? Food sources, but what's a factor that determines our ability to produce food?
Spatial barriers. How far without
You can build skyscrapers into space. What is going to... But how would we build skyscrapers up into space? Now resources in general will be a factor, but we can make resources stretch through efficiency. All of those things are tied to scientific and technological advancement. So, 500 years ago, we wouldn't have had the technology to feed 8 billion people. We do today. And technology is one of those factors that affects human population growth. versus, there really isn't any other animal out there
So
that.
you're basically saying we should all become scientists so we can all survive.
Well, we don't have to all become scientists and engineers, but I guess I would say, if nothing else from this class or from any of my classes, I would just like you to take away that science and science support and funding is definitely worthwhile. Okay, so basically by putting K at this point into this equation, we are going to take into consideration that how fast our population is growing obviously is based on the rate of growth and the current population size, but it's also going to be limited by this carrying capacity. And what we find, and I threw this chart in here, and I know there's a ton of numbers on it, but really I just want you to look at the trend right here at the end. In this case, we are assuming a carrying capacity of 1,500. Okay, so that's our carrying capacity. K is 1,500. And what you find is, as a population grows towards that carrying capacity, it is capable of adding more and more and more individuals to that population per unit of time, which is typically a year. But once you hit carrying capacity, the effective number is going to drop to 0. Okay? And if you look back at the equation, not to play with the math too much, but if your population and your carrying capacity are the same, what is this value going to be? 0, and you're multiplying it by these other variables, which is going to make it all 0. So the number of new people per time is going to hit 0. Mathematically speaking.
Which means you can't go any higher, but you're at the maximum carrying.
If you plot this function, you find that you will not exceed the carrying capacity. So you have a lag phase, an exponential growth phase, but then when you take carrying capacity into consideration, it's going to kind of somewhat asymptotically, I guess it actually just goes straight to it eventually, you're going to hit carrying capacity and stabilize there. Now, this is an idealized mathematical plot from a mathematical model. So what we'll find is that it's not always this simple. Here's what typically happens in a lot of populations. You have the mathematical logistic plot here, but in many populations, most, maybe all populations, I don't think any living thing is immune to this. The mathematical model is your theoretical, idealized scenario, but in real life, organisms are going to typically reproduce as much as they can. So in this population, this is a little microscopic critter named Daphnia. You can find them in the lake. We got lake water out and looked at it under the microscope earlier this year, didn't we? Yeah, some of you I think actually saw some Daphnia, but you may not have known what you were seeing. But if you look at the dots here, this plot's kind of a typical Daphnia population where it has a lag phase, exponentially grows, but then you notice it goes way above its carrying capacity and then crashes back down before stabilizing around the carrying capacity. Not every organism does this either. Some kind of boom and bust and fluctuate wildly, but typically at least around the carrying capacity. Now, I just want to go back real quick and look at this formula here. You will need to do a little math from time to time. The AP Classroom Problems for today has some mathematics that you're going to calculate with like this number or with this equation. This right here, this component of the equation is typically what you'll be solving for, and it represents this dn over dt. This represents how many individuals you're going to add to the population. You'll almost always be given a growth rate. You're typically going to be told what the population is right now, and you're probably going to be told what the carrying capacity is as well. So usually it's just pretty easy math where you're given R, given N, given a carrying capacity, and then they just ask what's the new population going to be? So if you have, say in this example, 1,000, actually we can go back to some real numbers. If you have something like 1,000 individuals and you know the growth rate and you know the carrying capacity, well, those are the only three variables you need. When you plug them into the equation, you'll get how many individuals you're adding to the population during that period of time. And you just would say, well, 1,000 plus 333, the population will grow to 1,333. So the math is not too confusing. So the only thing confusing, sometimes people will get 333 and they'll be like, so my population is now 333? No, it's 333 more than the population you had before that time period passed.
Is the hardest that math will ever become in biology, AP biology, around pre-calculus statistics level?
Yes, yes.
Okay, so it never gets up to calculus.
If you have any math on the AP exam, it's going to be math that we did in class with error bars, chi-square.
To be honest with you, the hardest math we've done this year was like the first or second class.
Yes, early on with some of the statistics is about as hard as it gets. And we can practice all of those different little mathematical manipulations that we've done this year. Okay, so life histories. This chapter moves on, talks about life histories. I just want to cover this briefly. Essentially, life histories are going to represent kind of the reproductive strategies of living things. Okay? And there's no real vocab here. I just want you to understand sometimes people kind of humanize all living things. And it's important to realize that as a human, you're one species with your own set of reproductive and evolutionary strategies. And not every living thing lives life like a human lives life. There are organisms that reach sexual maturity very young or very old or much later in life. So earlier or later in life. There are organisms that reproduce once and die. There are organisms like us that can reproduce throughout a large span of our lifetime. There are organisms that have thousands of offspring every reproductive event. There are organisms like us that have one, maybe two or three, if you have twins or triplets. So every living thing has some sort of life history, some sort of reproductive strategy. Some living things every year, like a lot of plants, dandelions is an example your book gives. Every year dandelions are going to produce thousands of seeds, which are their offspring, and just send them out into the world and hope that some of them land somewhere where they can grow and, continue the life cycle. Humans go pretty far into their life before they're capable of reproducing. Then we have a large span of time where we can have small numbers of offspring periodically. That is a very different life history, a very different strategy. And we typically assign two very general terms for a spectrum of possibilities. We have what are called K-selective and R-selective strategies. The K refers to what? Carrying capacity. And the R refers to the growth rate. So there are some strategies, some organisms that employ strategies that allow them to kind of hover around carrying capacity. There are others that employ strategies that kind of are more apt towards that exponential moment or time in the growth curve. So a K-selective strategy is typically like kind of low reproduction rates. You spend a lot of time carrying the child in pregnancy. You spend a lot of time raising the child and, watching it until it reaches some point where it's independent. It's typically a slower growth rate with more investment per child. Our selective strategies are like the dandelion or bacteria or insects that lay a clutch of hundreds of eggs at a time. Our selective is going to be kind of low investment per child with many, many children, maybe many, many reproductive events. Say again?
We're K selective.
Humans are much more K selective. Elephants, probably more so than humans. Whereas a lot of insects go for this R selective strategy where they just have hundreds of offspring and 1% are expected to actually make it to adulthood. It's kind of a quality over quantity approach. You should be aware, these are terms that if you take AP Environmental Science, these terms will come up, and they're terms that I could see being used in the AP exam if they ask questions about this unit. Okay. Section 5 of 6 of this chapter talks about density-dependent and density-independent factors that control population growth. There's not much focus on density-independent. It's really much more of a focus on density-dependent factors. Basically, density-dependent factors are things that affect the growth of a population that are a function of how big the population is. So usually when you talk about density-dependent factors, you're talking about things that when the population gets big, it slows the growth rate down. And I have some examples. Density independent are things that can slow down growth rate but don't really have anything to do with how big the population is. So I want to focus on just the density dependent ones, just so you're aware of them. When you have a big population, population growth rates can slow, and there are a lot of density dependent reasons for that. Disease can be more common in bigger, tightly packed populations. Resources become less common. So you have less food and water per individual, more disease and outbreaks of disease. You can also have the environment change and kind of, it says toxic waste. I don't want you to think of like nuclear waste, but just simply like, excretion that's laying around that needs to be dealt with, tainted water supplies because of excrement in the water. And you even have, this is a fascinating one, intrinsic factors. And I don't know if we totally understand this, but intrinsic factors mean within the organism and behaviors that the organism displays. Yes?
Would that be like the one child and 2 child policies in India?
In a human civilization kind of setting, you could probably put things like a one-child policy under intrinsic factors, but it goes a little deeper than that. We have found in like mice, for instance, if you pack a lot of mice in a small area and they experience a dense population, they just want to reproduce less. And I think we see that some in humans. In more dense populations, you tend to find people aren't as interested in having children and raising children. It's kind of a fascinating set of factors that's linked to how dense the population is. Again, you can have a huge population, but if you have plenty of space and resource and it's spread out, that's not high density. But if you think human-wise in a big packed city, that is where you would see density. So density is something that, of a population, is something that can slow the growth rates. There's also this issue of stability versus fluctuation. Not every population, as I already kind of mentioned, hits a carrying capacity and then just hovers around it. That's an ideal stabilized situation. I think most populations would suffer less if we could just kind of approach that carrying capacity and stay there. But you have a lot of predator-prey interactions that affect how much fluctuation you have around a carrying capacity. So this is a typical predator-prey scenario where you have wolves and moose. The wolves that are eating moose and relying on the moose for their food supply. And what you find, and it's not a perfect kind of function of one another, but you do see a general trend where when prey populations increase, that means more food for predators, so their population increases. But when you have a bunch of predators, it really starts to hinder the prey's growth rate. So a spike in wolf populations can actually cause moose populations to drop. Well, when there's less moose, what happens?
There's less wolves.
Wolves starve. So the predator populations can crash when prey populations dip. And then when there's less predators, that allows for moose populations to recover, predator populations follow. So there's a fluctuation a lot of times between predator and prey. And you see these kind of typical plots that come out of that. And then finally, at the end of this chapter, and the last thing I'm going to talk to you about is human population. This can get really complicated. There's a lot of economics that centers around this idea. The human population is unique, and check out our growth curve. This is from the dawn of civilization to now.
I want to see what it's like after, like pre-COVID, post-COVID.
Well, we probably won't see much of an effect because we are in the billions.
Yeah, and it's
So
only millions.
even a catastrophe that kills millions of people is a fraction of the population.
Yeah.
But check it out. We have, a fraction of a billion. We're talking about maybe around 100 million people around the world for the first kind of 10,000 years of civilization. Notice, and I can't explain every fluctuation, what do you think this kind of noticeable little dip is?
The bubonic plague.
That's the bubonic plague that swept from Asia all the way to Europe. Killed a third of Europeans. I don't know the fraction of other people in other areas that it killed, but there's a blip here that is the bubonic plague. But once you hit, what happens in the
1800s? Massive exponentiation outwards.
Well, there is a lot, like in the U.S., there's a lot of like kind of frontier colonization.
Yeah.
But what scientifically happens?
Light.
The Industrial Revolution hits, and we are basically capable of providing much more food and resource to people.
I feel like light was also one of the larger inventions because if you think about it, like starting cities and having light might reduce predators like trying to.
Yeah, well, it's just, there are many factors,
Yeah.
many technological
No, I'm not
factors.
just saying I'm saying it's one of the huge ones.
Yes, I mean, germ theory, Louis Pasteur, understanding disease, antibiotics. There's a long list, but we are definitely, what would you call this near vertical point on this growth chart?
Exponential.
We're at an exponential point of growth right now. Now, at some point, what has to happen?
An extinction event.
Whether we like it or not, it's going to have to level out at a carrying capacity, or we will wildly fluctuate around a carrying capacity. We have not really seen that yet, but we probably will. The last thing, I have 2 slides, but this is the last one that's related to actual AP material. These are age structure charts for 3 different countries. And I'm not sure what year, but this is into the 21st century. Being able to read these charts is something you'll want to be able to do going into the AP exam. You have color-coded males and females. Every bar or layer here is an age range. And the wider the bar, the bigger the percentage or proportion of the population of people are at that age range and gender. Here we have kind of your typical pyramid-shaped age structure chart, which in this case is the country of Zambia. This represents a lot of growth potential and probably very high growth rates because most of the population is in reproductive age or approaching reproductive age, and a small proportion is actually past the age of reproduction.
I want to see a building like that. Someone should make a building that looks like that.
Yeah, that'd be kind of neat.
Zambia.
The U.S., which is approaching what we call kind of replacement rates. So, it takes 2 people to have a kid. If your replacement rate is 2, that means every 2 people are having 2 kids and your population is stable. The U.S. is at 2.1, 2.2. We are very close to replacement rate, but a little bit over, so we're growing slowly. And you notice a pretty flattened set of bars here where every age range is roughly represented except, kind of the elderly range. And then you have some countries, this is Italy, where there aren't as many people approaching or at reproductive age, and it's a much older country proportion-wise to some of the other ones. This gives you an idea of how countries will grow and, kind of function in the future. There's a lot of economic concepts that can be related here. And just to give you an idea of that, what are some issues with, say, 70 and older? What are some issues you face as a country with those parts of your population? Their retirement. Maybe they can't work, or they can't work as hard or as long or as rigorously as they once could. Medical issues, nursing home care, things of that nature. If you have very few elderly people that need care and resources without, currently contributing as much kind of work and effort to the population, if that number is very small and you have a huge workforce to support them, there are a different set of issues and challenges you face than, say, if your elderly population is bigger. And in Italy, if I'm not mistaken, I believe, this may be 10 or 20 years ago now, I think Italy hit negative unemployment rates at one point in the last 10 or 20 years. And that's not a good thing. You want some unemployment because you want workers available to fill roles. When you hit negative unemployment, that means there aren't enough people here to even do all the jobs that your economy is asking. So work doesn't get done.
Oh, so that means there's space. There's like space where there's more jobs than there are people.
Yes, yes.
That's Japan's.
Japan is probably reaching that. Yeah,
Yeah,
is that
it's like
Japan's
an
age
axe.
structure? Yeah, this is very similar to the Japanese age structure
But
right
theirs is
now.
like really large in the 30 range, and then has a spike in like the 70 range too.
Yeah, and they fluctuate, and for every country, there's different reasons why they fluctuate.
They also have a lot more females, it seems.
And yeah, definitely older populations are going to be proportionally more female than male, just because males tend not to live as long, for a variety of reasons, including poor decision making. Finally,
We're stupid.
I wouldn't go that far. This is not part of the information for today, but there are 3 chapters in your book after this, all related to Unit 8. If you're ambitious and a real go-getter, I would flip through them. There are things that, good, valuable pieces of information that I'm not going to cover with you. I'm not even asking you to read them. But it certainly wouldn't hurt if you have the time to go through at least the bold-faced vocabulary and get an idea about some of the concepts that are covered in those last 3 chapters. So they're there, but they're not required. There is a 25-question AP classroom problem set. It is required. This is the one that or at least one of the ones that I'm not making optional. So with the time we have left, I want you to go onto the AP Classroom, and all of you need to attempt them. There is no test on this unit, so this is the only way you're going to see the styles of questions you might be asked, since I'm not giving you a test. So work on the AP Classroom, and the rest of this school year is either going to be our pig dissection week next week, or kind of practice written response or multiple choice questions to help you get ready for the AP exam. This was the last lecture. All right, such enthusiasm. Bye. Oh, that just turned my monitor off. I still have to stop the video.
Bye.
And